Text. National Museum of Natural History, Smithsonian. Hot Topic, a twist on ancient technology, fiber, string and more, featuring Bruce Hardy, Professor of Anthropology, Kenyon College. September 18, 11:30 a.m. to 12:30 p.m. Eastern Time. 6 close-up photos depict a variety of fibers. Briana Pobiner appears in the upper right corner.
Hi, everyone, and welcome to today's Hot Topic program, a twist on ancient technology, fiber, string, and more with Dr. Bruce Hardy. My name is Briana Pobiner, and I'm a paleoanthropologist and educator at the Smithsonian's National Museum of Natural History. I'm a brown and gray-haired woman in a green sleeveless shirt with pink polka dots, wearing headphones in front of a Zoom screen with an African savanna photo with grass and an acacia tree behind me. Whether this is your first time joining us or you've attended before, we're so glad to have you here. Before we get started, I have a few housekeeping notes. This discussion offers closed captioning. You can turn the captions on or off via the CC button, which should be located at the bottom of your Zoom interface. We are in a webinar format. We can't see or hear you. So as you have questions, please go ahead and submit them to the Q&A box, which is at the top or bottom of your screen. It looks like 2 speech bubbles, so we can sort through as many as possible. The Q&A time really flies by. The Q&A box is also where we will share any relevant links during the program, so keep an eye out there. We'll start with a presentation by our speaker, Bruce Hardy, and then I'll join him here to take your questions. During the presentation, I will also write answers to some of your questions, at least any that I can answer, as will another member of our behind-the-scenes team, Dr. Ryan McRae. So now I'd like to go ahead and introduce our speaker for today. Dr. Bruce Hardy is Professor of Anthropology at Kenyon College in Ohio. He is a biological anthropologist who studies human evolution and human ecology. Trained in paleoanthropology, he has worked extensively on the Paleolithic of Europe and Africa, particularly with early hominins and Neanderthals. He has also published evidence for the earliest known manufacture of string 50,000 years ago by Neanderthals. And now I welcome Bruce to share his presentation.
Bruce replaces Briana in the upper right corner.
Hello, welcome everybody. I'm Bruce Hardy. I'm wearing a plaid shirt with red in it and beard and glasses and am in front of a peach background. So I'm here to talk to you today about fiber and string and all these things that we don't tend to think about. So when we think about Paleolithic archaeology, most of the time we're thinking about stones and bones because that's what we find. But if you take a minute to look around you, you'll see that there's a lot of things that are in your current environment that would never survive archaeologically. The clothes that we're wearing, the desk you may be sitting in front of, the rugs or curtains that might be around you, all these things. Even the house structure that you're sitting in is often made of wood, and this stuff might not survive. So we're missing a very large portion of the lives of our ancestors and that's what we're trying to reconstruct. So I want to talk about perishable technology, but in particular, I want to talk about string. First of all, we have to figure out how do we make string, because for the most part, the people that are listening to me right now have never made string. You've bought string, you've found string, but you've never sat down and taken a plant, extracted its fiber, and made it into string. So the first thing we need is fiber.
Bruce, I just want to make sure, did you mean to share your screen already?
I didn't have to, I am now sharing it.
Perfect. Okay. Wonderful.
I am now sharing it. That first part was intro, but we are at the wrong place.
Bruce's slide deck opens, displaying numerous small thumbnails.
There we go. There we go. Okay.
2 bundles of greenish-brown string appear.
So we need to think about string. Here's some string here that I've made, sitting on a porch that needs to be painted. But you got to think about fiber before you can think about string. So where do we get fiber? Well, there's a lot of different plants that are useful for producing fiber, and I'm going to highlight 2 right here because they're readily available in my environment here in central Ohio.
2 piles of fibers, one green and one brown, appear to the left of photos of stinging nettle and basswood plants.
The first is nettle. So this green stuff over here is all stinging nettle, And the stinging nettle is normally something that we try to avoid, but if you grab it at the bottom and strip upwards, you can get rid of that stinging stuff, and then you get nice fiber that you can use to make cord. Next to it is some basswood fiber. Now, this is a little bit more difficult to come by. Here's the basswood tree over here.
He gestures to the brown fibers, then to a photo of the basswood tree's green leaves and tiny white flowers.
But to get the basswood fiber, you actually have to go and get the inner bark. And this is myself and some of my students here taking a branch of a basswood tree, and we're stripping off the outer bark, and then this white stuff in here is the inner bark, and we're going to have to get that off of there in order to get the fiber to make string. And as I started to put this talk together, I started to get a series of slides here that showed the next thing we did was to peel the bark off and then do all this stuff. But then I realized that maybe since I had an old video of this, we just let Louis Leakey show us how to do it. So what I've got here is a video that I'll show you in a second. We're going to watch about 3.5 minutes of this video. It's a little bit blurry to start with. It cleans up a little bit. But this is actually from 1975 from a documentary called The Legacy of LSB Leakey. And it happens to be Louis Leakey talking about perishable material and cordage. And in the space of 3.5 minutes, he's going to go from a tree to a snare, which is pretty impressive, better than I can do. So give me a second to get this to the right location.
The video clip plays. Aerial footage captures a dry, flat landscape sparsely dotted with shrubs and trees.
For a time, he learned to walk upright and so freed his hands for making tools.
A bird perches on a leafless branch.
And after he developed more and more brain power, he began to start thinking and planning how to use other things around.
Louis Leakey pulls a leafy branch off of a tree.
Unfortunately, most of those things are perishable materials, and we have no perfect record from the materials themselves of what he used. But we can guess a good deal, probably accurately, from the things that he caught.
A wide-eyed bunny sits beside a thorny bush.
We know he must have caught fish because we find fish remains and remains of small animals that he snared on the living flowers.
Louis carries several branches as he walks through dense vegetation. A gazelle-like creature stands among trees.
And so we can begin to guess that as his hands became free and more capable of precision work, then we're pretty certain one of the things he first started to do was to make cord.
He tosses the branches on the ground.
You see, you can make cord just with nothing but your bare hands. You go into the bush, you can pick the necessary wood, cord making, out of bark, without any weapon at all.
He sits in the grass and manipulates the branches.
And then, having done that, it's just a matter of peeling the bark from the saplings, a very simple action like that, and then separating the outer bark from the inner bark, because the outer bark is terribly brittle, and the inner bark is not. It takes a little learning how to do it, but you can separate the outer bark from the inner bark, and once you've got that separated, then you've got the perfect material for making really strong cord and string and twine that's suitable for any of the purposes you could possibly imagine the man might want it, plaiting, snaring, and the rest. Now, having got his inner bark separated out, next thing was simply with his fingernails to fray it off into thin strips. This is material of the most extraordinarily strong and durable nature, especially when it's been turned into actual string. This same stuff has to be frayed a little. A man had in his own teeth the most perfect decorticator. Nowadays, of course, this sort of thing is done by machinery. But with his hands and his teeth, possible to fray that inner bark.
Louis chews on a thin strip of inner bark to separate it.
Quite reasonably well. And then comes the last stage. Also looks and is, in fact, very, very simple. Separate them out into two separate groups.
He holds 4 long, thin strips of bark across his lap, then rolls them together.
And then proceed as follows. Quite simple.
The strips roll and twist around each other to form 2 long cords.
not as easy to do on one's trousers as it would be on a bare leg. But I'm rather a bit too hairy for that.
He rolls the cord back and forth over his khakis.
By that process, doing very nicely. Now, you can roll your cord up and produce a twine of any thickness you like. And there, close up, you can see the way the cord is.
In close-up, the fibers twist around each other.
Now, if you want to make it thicker, you make it as thick as a rope. And with this sort of thing, man could make his boulder stones as weapons of offense for attacking animals at a distance. He could make snares and traps, even snares and traps big enough to catch quite large animals.
He loops the twine into a knotted triangle shape and dangles it low to the ground, forming a snare.
He had, in fact, something available, requiring no tools to make it, which made him even further master of his environment.
Lewis stands up and walks away. The video concludes. Text. S twist clockwise, Z twist counterclockwise. Direction of fibers. A diagram depicts cords with fibers in S, Z and I formations.
So there you have it. Cord in 3.5 minutes, and Louis Leakey makes it look very easy. He's a bit practiced at doing it, but what exactly did he do? That was pretty quick. So I want to go through and kind of go step by step and explain to you sort of what he's doing. The first thing that we need to think about when we're talking about cordage here is twist, because that's what we're doing is we're making twisted fibers. And you get terminology used to describe these twists. So if you twist cord or a bundle of fibers clockwise, if you twist them clockwise, it'll produce a diagonal that is similar to the diagonal of an S. It goes from the upper left-hand corner to the lower right-hand corner if you look at the way the direction of the fibers go, just like the diagonal of the letter S. If, on the other hand, you spin them counterclockwise, then you produce a diagonal that is similar to the letter Z from the upper right to the lower left. And when you're making cord, you're actually going to end up alternating S and Z twists in order to get something that doesn't unravel.
A diagram on the left depicts figures 6A, 6B and 6C, which demonstrate the process of making cord. Figure 5 displays the blending of S and Z twisted strands to make a Z twisted 2-ply cord.
So it looks something like this, and over here is what Leakey's doing here. So here are the two strands or bundles of fiber that are going to become strands here that he's separated out on his leg there.
He gestures to 6A, which displays two ends of strands in a left hand, as a right hand applies upward pressure, further twisting the fibers in a clockwise direction.
And he's rolling his hand away from himself, and what that's doing is creating a clockwise twist. At that point, he rolls his hand backwards the other direction, and those two now S-twisted strands twist back around themselves to create a Z-twist. So that over here you can see that you've got the strand itself which is S-twisted, and then the cord which is formed, which is Z-twisted. So you can see here the upper right to lower left diagonal that you're getting here. And actually the cord kind of wants to do this on its own. When you roll it away from you like that, if you let go where your fingers are holding it up here, it's actually going to twist on the Z all by itself, at least if it goes correctly. So what we have then here is a Z-twisted 2-ply cord with S-twisted strands.
4 strings stretch across a wooden deck.
Here's a bunch of string that my students made from nettle, but most of it is 2-ply. Most of the time you get 2-ply. We'll talk about that later. So this is similar at the same kind of twist that we're getting with what Leakey's doing here. You may note that there's some gaps and things in here, and that actually has to do with the fact that they were working this material very fresh. We had just harvested it. And so then as the fibers dried, they shrunk, and you've got this stuff here. Which is not the best thing you want to do. You might want to dry it out a little bit. Leakey didn't do that. I'm not sure how the bast that he was using is working. But Leakey makes it look easy. For bast, for that inner bark, you sometimes need to use an extra step in there where you take it and you strip it off like that. Or if it doesn't want to come off very easily, you take it and you do what's called retting. You put it into the water You submerge it in water and kind of weight it there, and you leave it for a couple weeks to break down some of that interstitial tissue in there so you can break it out into fibers. You also have to know when to do that. Here in central Ohio, the best time to go for bast is kind of the last 2 weeks of January. Excuse me, last 2 weeks of June. Last 2 weeks of June. January would not be a good time to go for it. You want to wait till the sap is rising in the tree and the new bark is forming. That's when it's the best time to do it. You can do it other times a year, but it doesn't work as well. And of course, once you have cord, you can do all kinds of cool stuff with it. You can take it and use it as a binding to help attach a stone tool to a haft, which of course is something that we're interested in for the time periods we're talking about.
Cord attaches a carved arrowhead to a wooden haft, forming a spear. In another photo, two people hold a makeshift raft.
Or you can make a raft out of it, or in this case, sort of a raft. This is a picture from the pandemic times when I was trying to figure out ways to entertain my children, and I sent them out in the woods and told them to make some cordage and make a raft, and they got tired of making cordage. So they made a little bit of a raft and floated a rock, a piece of flint across the river, which is good. I bring this up for a particular reason for something else I'm going to show a bit later. But you can then, with simple cord, you can combine it to make all kinds of things.
An image on the left displays a craft made of loop cord. A photo on the right depicts a net made of milkweed cordage. Text. Net, Danger Cave, Utah, milkweed cordage. National History Museum of Utah.
Here's what is likely some cattail. So it doesn't make a great cord, but if it's thick enough, it'll work pretty well. And you're using a simple looping technique here to loop it around each other to start creating what could be a net or a bag. Or over here on this side, this is actually an archaeological piece from Utah, and it's made of milkweed cordage. Milkweed is another good source of fiber. So is dogbane and a couple other things like that. And this is actually knotted together, so you're tying knots in these areas to make a nice net. Very, very useful for catching all kinds of game and fish and other things.
A hand holds a net bag with a large flint inside.
This is a bag that we produced out of nettle cordage. Again, we've got a lot of nettles around here. And I've taken and put a piece of flint inside it to kind of show you the shape of it, but also to illustrate one of the things that this allows you to do is to do things like carry rocks around. We know our ancestors are using a lot of rock. And if you ever try to carry a whole bunch of rock in your hands, it's not very helpful. It's not very useful. So having something that you can carry things in is of course going to be advantageous. Just as an aside, this particular bag right here probably contains about 80 feet of nettle cordage. You start putting these things together and it takes a lot in order to do it. Well, that's all fine and good. Cordage is useful, but can we find it archaeologically? And fortunately, the answer to that is rarely. Yes, we can. So to talk about this, we have to turn to a site that I've worked on for a long time in France called the Abri de Maras.
Text. Abri du Maras Neanderthal Site, Level 4, 42 to 51 Ka. Two maps display close-ups of a third map of France. Rivers stretch across all three maps.
This is a Neanderthal site in the Rhone Valley. It's down here near the confluence of the Ardèche and the Rhone rivers.
He gestures to Maras just north of the Ardèche River.
We're interested in one level. There's multiple levels to it. That's called level 4, and that dates between 42 and 51,000 years old. Now, the research that I do involves using microscopes to look at stone tools, because when we have stone tools and you take a stone tool and you chop something up with it, you cut something with it, bits and pieces of what you're cutting up stick to the stone tool, and you can sometimes find those later. That's what I'm interested in looking at. Here's some other examples from tools from Maras itself.
Text. Residue analysis. Figure 12 includes 3 close-up images of fibers in the upper left corner. He gestures to the rightmost image C.
These are feather barbules over here. There's a series of nodes and prongs that tell you that that's what that's coming from.
He gestures to a cycloid fish scale fragment in figure 13 in the upper right corner.
Fish scales. Again, both of these things, birds and fish, are not abundant at the site because They're both small animals with very fragile bones. They don't survive very well, but we are finding some stuff on the stone tools.
He gestures to figure 8, a rabbit hair in the lower left corner.
This is actually hair that's also on the tools at Morass, and it's actually a rabbit hair. You can tell from the dumbbell shapes cross section here. We also found cut marked rabbit bones at the site. Nice to have multiple lines of evidence that kind of come together.
Photos G and H in the lower right corner depict cut rabbit bones. Text: crushing and spin-off impact fracture, possible use in complex projectile technology.
Well, where does string come in?
Text: Abri du Maras twisted fibers. 5 images depict twisted fibers in close-up.
So after looking at a whole bunch of tools, I started noticing that I was finding some fibers that were twisted on some of these tools, like the pictures that I'm showing you here. Normally I discount twisted fibers that I'm finding on archaeological material because it's likely coming from clothing, like my shirt here or something like that. But in that case, it's usually dyed, and it's usually not really, it's sort of sitting above the surface. It's pretty easy to identify when it's a modern contaminant. And this stuff didn't look like that. And some of it was actually multicellular, so which is not what we're making clothing out of. So I was like, so we published something and we said maybe they're making string, but it really wasn't good enough for us to say, yeah, this really is string, until I finally got to this piece. So after several hundred tools have been examined, I looked at this small flake. It's about 5 centimeters long, a little bit longer.
Images depict a sharp, pointed flake's face, back and side. Text: Levallois flake, G8128 level 4.2 with adhering cord fragment. Photo by M. H. Monsell.
And on the inferior surface, so the surface that was sitting on the sediment, would have been falling on the ground there, there was this fragment that you can see right here, this kind of white spot right there.
His mouse runs over a boxed section of the flake's inferior surface.
And I was like, oh, this is interesting. This tool was stratified originally under about 3 meters worth of deposit. So it had been down there for quite a long time. Nothing had been disturbed until we did the excavation. And when we started to look at this, it turned out to be a piece of string.
6 close-up images of the same string appear, labeled A through F.
So here's some of the pictures of the string in different forms of microscopy.
He gestures to black and white photo A in the upper left corner.
So over here, this is an SEM, so a scanning electron microscope photograph of the piece of string.
He gestures to a brown-toned Helix photo B in the lower left corner.
Here's one taken with an optical microscope, but one that's called sort of a 2D, 3D platform, which stacks things together so you can see better what's going on. But it's all one color, and it's kind of hard to figure it out. And it took us a long time of examining this stuff to see what's going on.
He gestures to sketched drawing C in the upper middle.
That's why we have this drawing here, and then this colored photograph.
He gestures to the enlarged, highlighted Helix photo D in the lower middle.
And it turns out that, very similar to what we saw Leakey making there, we've got strands here that are S-twisted, and then those strands are Z-twisted around one another.
He gestures to fibers in the sketch, then in photo D.
And you can see here the Z-twist, upper right to lower left. And I'll show you another picture to show the S-twist a little bit better on the next slide. But the other thing that we were able to tell, looking under the SEM, is you can see that we've got these individual fibers here, and they've got pits in them.
He gestures to a SEM photo of bordered pits, photo F in the lower right corner.
These are referred to as bordered pits, and it allows us to identify this as coming from a conifer, either a pine or a spruce or juniper, the bast of some kind of conifer. We can't tell which one, but it's pretty good to be able to figure out that much.
In the upper right corner, SEM photo E depicts bordered pits circled in red.
Looking at the next picture, this is kind of a close-up that's going on.
Text: Figure 4, SEM photo of 3-ply cord. First close-up shows Z-twist of strands, image rotated 90 degrees counterclockwise for clarity. Second close-up shows S-twist of fibers within a single strand.
If we start down here, this is one of the individual strands, and all this stuff is starting to unravel because that's been around a while.
He gestures to the S-twisted strand near the bottom of the image.
But you should be able to see some of these fibers that are going across this way.
He gestures horizontally across the S-twisted strand.
And you see the S diagonal from the upper left to the lower right.
He gestures to the Z-twisted strand near the top of the image.
And then up here, this is from this section up here toward the beginning, again, you get that Z diagonal coming this way from the upper right to the lower left. So what we have here is a 3-ply Z-twisted cord with S-twisted strands. And that's different from what we saw before because it's 3-ply, not just 2-ply. So we've added an extra set of strands in there, which is going to make it much stronger. Well, what are the implications of a 3-ply cord?
A 3-plied twisted cord rests on a table.
This, by the way, is a rope that was sitting around my office that I found the other day. It's from Lowe's. It's the exact same makeup as the string. It's a 3-ply Z-twisted cord with S-twisted strands. It's the same thing. It's bigger, obviously. But if we start thinking about what does this mean in terms of cognitive abilities, the Neanderthals who made this had to have a detailed ecological knowledge of their environment. They had to understand things about trees. They had to understand things that you could have, that strip different parts of trees off to find fiber to make this stuff. It also implies that they have an understanding of sets and pairs as you get these bundles of fibers matched together, which implies some understanding of numeracy. We also think about it as an infinite use of finite means from a cognitive perspective. These steps, I can keep building on this over and over and over again and make the biggest rope that I want to, or start combining these elements together with knots and other things like that, and I can build outward and outward. There's no stopping what I can do. And then finally, the complexity of a string actually is similar to the complexity of language. Think about it this way. You can't have a sentence without words, and you can't have words without the sounds that make up the words. I can't skip to the end. I can't skip to a sentence without the other pieces in between. I can't skip to a cord or a rope without understanding all the pieces that have to happen in the middle. So in that way, there's the same kind of cognitive scaffolding that you have in language, which of course I think Neanderthals did have. Now, this is probably not the first cord. I think our ancestors are probably making this technology much, much earlier. But it's the earliest surviving evidence that we have of cord. And I want to bring up one other interesting implication that we don't have direct evidence for, but we may be able to kind of hypothesize here. And that is boats.
6 sketched figures labeled A to F depict a variety of boats and rafts. A depicts a single rider on a standing raft. B depicts multiple riders on a flat raft with a sail. C depicts 2 riders in a boat with gathered ends. D depicts 6 passengers in a long, narrow boat with upturned ends. E depicts a single rider in a wide boat with a pointed tip. F depicts 6 riders in a long, skinny dugout canoe.
Once you have string, you can tie things together and you can make boats. Okay, fine. Yes, I can make a boat without string. I can make a dugout canoe down here like this one, F in the figure here. Yes, I could do that. Takes a lot of work. Have to have fell a big tree. If I got string, I can tie things together and make a raft. I can tie reeds together, cattails and things like that to make a boat. I can make bigger boats. I can even make big fancy boats like this one that have sails. All this is from twisted fiber technology. Well, how do we know anybody might have had boats?
Text. Figure 10. Map of archaeological evidence for Pleistocene water crossings in the Mediterranean. Artifacts in association with direct dating marked as filled circles. Sporadic undated surface finds with purported Paleolithic and Mesolithic attributes marked as hollow circles. For color legend, please refer to online version of the article. A map includes orange, red and green dots over various locations along the Mediterranean Sea, including green dots on Sardinia and Sicily, orange dots on Kythera and Alamnisos, and red dots on Crete, Naxos, Kefalonia and Zakynthos, as well as other locations.
Well, we look at where sites are. And this is a map of the Mediterranean. We could look elsewhere, but this is looking in the Mediterranean. And you see on islands that are always insular, that never actually touch land, even at low sea levels when land ice was really widespread, you're having to cross a good distance to get to land. Um, I'll highlight Crete over here. You've always got to go at least 25 kilometers, even at the lowest sea level, to get to Crete. And we've got Middle Paleolithic, that would be Neanderthal, and even possibly older sites there.
A map includes a variety of colored dots scattered over Greece, along the Ionian Sea. The island of Kefalonia appears just northwest of the island of Zakynthos.
The Greek islands of Kefalonia and Zakynthos are similar. You have to cross at least 5 to 10 kilometers of open ocean, which fine, you could swim if you want to, but making some kind of raft, making some kind of boat is probably going to be necessary. And we can, if we took in currents and other things, we could talk about why something more complicated than a raft is probably part of it. So that's what we can learn from morass. What other evidence do we have of fiber technology in the archaeological record? Well, before the publication of the string, some of the best stuff we had here was from Gravettian sites in the Czech Republic.
Text. Gravettian, approximately 28 Ka, impressions in clay. An image on the left titled Pavlov 1 depicts a piece of clay grooved with fiber impressions.
Now, what was happening here is they were making clay figurines. This is about 28,000 years old, and they had impressions of fiber in clay. Now, this one is from the original, so don't mind that this looks a little bit blurry. But these grooves that you see here are impressions of weaving.
An image on the right titled Dolna Vistanis depicts a basket-like weaving.
Over here, we've got a reconstruction of it, of this piece right here, and you've got warp, the vertical pieces here, and then you've got weft with over and under weaving. Clearly, this was not the first time somebody did this.
Text. Figure 4. Netting from the site of Zarask, Russia, original impression, microphotograph, schematic. The figure includes a photo of a 5 cm impression of a net in a piece of clay. A larger impression appears to its right, and a schematic of the net appears below.
This is another Gravettian site called Zarask in Russia, and again, we've got impressions in clay. You can see the grooves up here. This is actually the impressions of a net, also about 28,000 years old.
A Venus of Willendorf figurine measures 5 cm wide. The carved stone has a textured, faceless head, large breasts, a rotund belly, and an exposed vulva. A top-down photo of her head reveals its woven fiber-like texture.
We can even turn to things such as the so-called Venus of Willendorf, which is about 26,000 years old, and the Venus has a head that's been decorated here in some way, and this could represent some kind of headgear made from twisted fibers, maybe even some kind of knitting or some kind of woven piece that's there. More recently, published last year by Nick Kennard and Veerley. Oh, sorry, I got ahead of myself. This is older, found in 1959 at the site of Lascaux, so a famous cave art site in France, at about 17,000 years.
Text. 3-ply cord, S-twist, Z-twist. A figure depicts close-ups of 2 rope impressions in clay.
And here we have the impression of a cord or a rope in clay again, and we can see what it looks like. This is a reconstruction over here.
A reconstruction of the cord appears to the right.
Guess what? It's the same as the string. It's a 3-ply cord, Z-twisted 3-ply cord with S-twist strands. Bigger, but it's the same thing. So now, last year, published from the site of Hohlfels in Germany by Nick Kennard and Veerley Rutz. This is a piece of ivory from Aurignacian levels about 36,500 years old, so associated most likely with modern humans.
Text. Aurignacian rope making. Hohlfels, Germany. Perforated baton, ivory. Approximately 36.5 Ka. An image depicts an ivory baton with 4 holes drilled through it.
They're calling it a Lochstabe, or a perforated baton. But what they think this is actually a tensioner used to make rope.
3 people work together to twist cattail fibers into a rope. They weave the twisted fibers through holes in a baton.
And here they are working on stuff experimentally. So this is cattail, and you've got the three people on the right side of the perforated baton here, twisting things clockwise to create an S twist, and then pulling them through and going back the other direction to make a Z twist.
He gestures to a photo of the finished rope on the right.
And here's the rope they produced over here in the space of about 10 or 15 minutes. Same thing as the cord. 3-ply Z twisted rope with S twisted strands. So what does this tell us overall about all of these ancestors in the all of these are ancestors in the Paleolithic? Well, I think it really means that you would even see a tree differently. Now, this is taken from Linda Hercom's work on Bronze Age salt mines, and it's just a good example.
Text. Figure 1. The exploitation of trees used in the Bronze Age salt mines, Hallstatt, Austria. Source. Hercom adapted from Grabner 2009, 225. A sketch of a tree indicates the diameter of wood used for various purposes. The tree's base, measuring 25 to 35 centimeters, is suitable for trugs/buckets. The tree's middle, measuring 15 to 30 centimeters, could be used for lighting tapers. The treetop, measuring 5 to 20 centimeters, could be used for scaffolds/staircases.
You look at a tree, you're not going to see a tree, you're going to see things that the tree can be used for. So in this particular example from the Bronze Age, maybe buckets made from the base of the tree, maybe lighting tapers from the middle parts of the tree here, and then up here, scaffolds and staircases from these other branches.
He gestures to the base of the tree.
Throw it into the Paleolithic, throw it into our Neanderthals, and maybe what you're seeing is you're looking down here and you're going, aha, we can strip bark off of this and we can get fiber to make string and to make rope or nets.
He gestures to the upper portion of the tree.
Hey, and maybe this part up here, maybe we're going to cut that and we're going to make into spears or handles to go with other things. Ultimately, it would have become an indispensable technology as soon as our ancestors figured it out. We haven't touched the beginnings of it. It's got to go back further than this. And finally, just the way we don't give credit for this kind of technology. I'll end on this meme that my wife found the other day. She does a lot of knitting. A random reminder, if your apocalypse team does not include shepherds, spinners, weavers, knitters, and sewers, you're probably going to die of hypothermia before you get a chance to build your Viking longhouse and all that other stuff. Fibers are important. Perishable technology is important. We should be paying attention to it. So, thank you for listening.
Briana returns.
That was excellent. Thank you so much. And we have started to actually generate some behind the scenes questions as you were talking. So I think we'll kick off with those while other questions come into the Q&A. So the first question is, do these different plant-based fibers differ in their resistance to decay in the archaeological record? Or do you think sort of all plant-based materials basically like decay and disintegrate on the same timescales involved in our prehistory?
Bruce.
Okay, this is going to be somewhat speculative because we don't have the kind of experiments that can show us exactly what's happening there.
Mm-hmm.
The bast that's coming from trees is going to have more lignin in it.
Okay.
The part of the molecule that makes it stiff.
Mm-hmm.
He presses his palms together.
And so probably that's going to be a little more resistant to decay than you're going to get with soft plant material that's not got lignin in it. You can think about just decay in general. A piece of wood is going to decay slower than a leaf or a stem that's not woody. But how much slower, it all depends on the conditions. But that would be my first thought on answering that question.
Okay, awesome. I have one more follow-up behind the scenes question before we go to audience questions. So would something like animal sinew or animal-based fibers be more or less resistant to decay? Like, might we expect that to last longer? Do you have a good sense?
So you can do the same thing. You make cordage out of animal fiber, and we certainly do yarn, and everything that we make from wool and all these other animal fibers is the same exact process as what we're talking about here.
Mm-hmm.
Or at least you can do it that way. Sinews are tough. Sinews are collagen.
Mm-hmm.
Briana nods.
And so collagen preservation is difficult.
Okay.
Even within bone, it doesn't preserve very well. Again, all this could be, we could have exceptions from this if we get
Mm,
something that's incredibly waterlogged or something that's permafrost. Because
right.
all these materials could survive in sort of extreme conditions like that.
That makes sense. Yeah, that like context of preservation is really important. So Shannon asked, what is the earliest example of basketry?
Well, that's interesting. So the earliest basketry and weaving are kind of related things because
Okay.
weaving, it's the same process. We're making a warp and a weft and we're going through. There's other ways to, there's more techniques to do this. So
Hmm.
the stuff that we're seeing there from the Gravettian, from the stuff I showed you from the impressions in clay,
Hmm.
that could be something woven. If it's stiffer, it could be a basket.
Okay.
So if it's from stiff material, we would call it a basket. If not, we'd call it a net or a bag or something like that. When ultimately they're the same thing, just one is less pliable than the other. So that could be the earliest stuff. I
Hmm.
will kind of just hint at the idea that we're working on some stuff from older levels at Maras, stuff that's older than 90,000.
Bruce crosses his fingers.
Stay
We
tuned.
might
Exciting.
stay tuned. We might there might be something along those lines. We'll see. We'll see. We don't have anything quite good enough yet. It's like looking for the string. We had to wait until we really found that structure before
Hmm.
we could really make that argument.
Okay. Ooh, exciting. Thank you. Next question from Shi Sia asks, what do you think are the ecological or cultural reasons why some cultures developed woven textiles and others developed bark cloth? They said watching Jason Momoa's Chief of War drama recently.
Huh. That's interesting. I mean, in both cases, I don't know nearly as much about bark cloth, um,
Okay.
but it's going to be certain types of trees that shed their bark pretty easily, and that bark is resistant enough that you can make it pliable without it breaking down.
She nods.
Mhm.
And it could be that just it could be an ecological difference that you're in an area where you've got things that are better for making bark cloth, so you get this
Mhm.
tradition of making bark cloth. And
Mhm.
in other areas, like where what I'm thinking of in terms of stuff around here, maybe you could turn some birch, which we have very, very little of, into bark cloth. I don't know that the basswood and the pine and other things like that that we have here are possible to do that with. So I can't think of anything that I could go out here today
Mhm.
and make bark cloth out of. So it might be an ecological difference.
Yep.
It might be a cultural difference. When you start a certain practice, that practice continues.
Mhm.
But I'm not familiar enough with bark cloth to offer anything concrete on that.
Okay. No, that's great. Thank you. So Eric asked, what is the age of the oldest fish hook, and do we have any Paleolithic fish hooks with attached line made of fiber?
We do not have any Paleolithic fish hooks with attached line made of fiber. The oldest fish hooks, well, you've got not if this is not a fish hook, you've got a barbed harpoon-like thing
Hmm.
from 90,000 years ago from Democratic Republic of Congo.
Hmm.
And that's the earliest stuff I know of that is a tool that's probably specifically used for getting fish. Um,
Yep.
Fish hooks are going to be much later. I'm
Hmm.
trying to remember. I'm thinking there's some stuff out in Asia that's maybe, I want to say 10,000, but don't quote me on that. That's just a different thing. You also don't need, obviously, with fiber technology, we don't need hooks to get fish. If we've got
Hmm.
nets, we certainly got fish, and you actually don't even need anything but your hand to catch fish if you know how to do it. Lay down on the side of a river, wait for the fish to come up, throw it on land, you have a fish. No, I've never done that.
I haven't either.
It'd be cool, but yeah, I know it exists,
Challenges.
but not me.
Cool. Thank you. Linda asks, to the extent that we're finding evidence of tools and debitage from, say, 8 kilometers away and from 100,000 years ago, is this implicit evidence that some form of fiber-based carrying technology existed back then? How about the need to carry babies long distances or even day to day while foraging?
There have been people who have suggested. I mean, look at Louis Leakey that we watched. Eh, No evidence there, but he's like, you've got to. First thing man would have done is start making cordage.
Mm-hmm.
You can. It's not a difficult inference to say that early on bags and nets and carrying babies and all these things would have greatly benefited or been aided by having this stuff around. I wouldn't be surprised if it's not a very early technology. There's a difference between kind of logically deducing that this would be helpful and showing that it actually happened archaeologically. Fire would have been
Mm-hmm.
great too. Fire is a great thing. Did fire really start 2.5 million years ago? Well, maybe, but we kind of need to show that it did before we can just assume that it was
Yeah.
going to. So I think it's likely that you could go very old with it, but is different than demonstrating that you did.
Yeah, that's fair. Um, Mike asked, I may have missed it, but in the archaeological record, what is the oldest evidence of string being used? And do
Okay.
we know anything about which hominin made it?
So what I stuck with stuff that was more directly evidence of string, either the impressions of it or the string itself. Inferring string from other artifacts, probably beads or what are thought to be beads. So you got Neanderthal stuff as old as 115,000 from Cueva Anton in Spain,
Okay.
which is shells that have holes perforated in them, and they've got some wear on the shells, and they were probably strung into some kind of bracelet or necklace on something.
Mm-hmm.
What that was that string? Was it a piece of leather? Was it sinew? That's harder to know for sure.
Mm-hmm.
That's probably the earliest evidence. There's a few things that are earlier than that, but I don't think the dates are really great. And some people dispute the 115 at Cueva Anton because it's based on uranium thorium. But I'd say 75 to 90 other beats
Okay.
in the Org Nation of Northern Europe and other places. Iterian.
Okay, thanks. So Denna asks, what does future research on fiber technology look like? Do you anticipate anthropologists making it a more common practice to look for perishable materials?
I certainly hope so.
Mm-hmm.
One of the things two things I was struck by when I was preparing this talk. One, watching the video there with Leakey, the old documentary, and him 50 years ago saying, "Hey, this would be commonplace." And then somebody asked me about basketry. James Adovazio, primarily a North American archaeologist who's done a lot of work in fiber, wrote an article a few years ago of 50 years of basketry. And in that article, he complains about the fact that perishables still don't get the attention they deserve. We still
Mm-hmm.
focus on animal remains and stone tools. If we're going to push the boundary of our knowledge, we need to find ways to detect perishables. So I think that admittedly, other people called for it 50 years ago. I'm calling for it again. We need to do
Mm-hmm.
more with it. We need to find that this is the untapped frontier.
Mm-hmm.
We got we got museums full of stone tools and animal bones. They're
Mm-hmm.
cool. And the stone tools are useful, but we got to start looking at them microscopically because that's where I'm finding stuff.
Do you think it's a matter of not having, I'm just going to follow up with my own question, not having specialists who do this, not having so sort of the awareness of like, the methods, not thinking to, not clean artifacts off, like what, not knowing the protocols to excavate in ways that this stuff would be preserved? All
Some
the
of it is
above?
some of that is the lack of specialist knowledge and the lack of you don't see many people doing what I do.
Mm-hmm. Mm-hmm.
Worldwide, there's not many people doing residue analysis of stone tools.
Mm-hmm.
The other thing is where I start this talk is explaining how to make cordage.
Mm-hmm.
We don't have the knowledge of what it would take to even make a lot of these perishable materials. We don't know how to do it. And therefore, it's not in our mind to think about.
Yeah.
That's why I start the talk with, okay, here's how you make a string. Because we
Mm-hmm.
just pick up a string and go, hey, I've got string. I went to Lowe's and got string.
Nice. So Madeline asks, for clarity, is strings construction limited to 2 or 3 strands in an S or Z twist, regardless of location and time period?
No, no, it's
Okay.
not. And it doesn't have to be the S twist first and then the Z twist. In fact, thinking about it and watching all these things where we came up with S and Z twist, it probably has a lot to do with the fact that us and Neanderthals and others are probably predominantly right-handed.
Oh,
Because
yep.
you're putting it on the right leg and you're rolling away from you. If I put it on the left leg and I rolled it away from me, it would be the opposite. It would be a Z twist.
Okay.
Back the other way. But the number of strands is just the number of pieces you want to work with. The more strands you put together there in the first place, it gets a little more complicated. It gets a little trickier.
Mm-hmm.
But you can also do things like with the tensioner that I showed you from the ordination, make more holes, make a bigger rope.
Briana nods.
And it's all just about, and then you can, besides that, you can make a couple of the 3-ply strings that we did, and then braid them together, and you're building up things bigger, and you don't have to do it all in one go.
Okay. Does the number of strands, is it directly related to the strength, or is it really more the raw material? That's my own question.
Well, the raw material definitely plays a factor. The basswood, the bass from pine is much stronger than anything from nettle.
Okay.
It's just more durable. It's stronger. But beyond that, the number of strands makes a huge difference. If the more strands you put in there, and the other thing that makes a difference for strength is the length of the fibers.
Okay.
The longer the fibers are, the stronger the rope is going to be, because this is all about creating friction. So by twisting those fibers together, the tighter you twist them and the more you twist them, they can't pass by each other.
He makes a twisting motion, then hooks 2 fingers together.
They can't, they're stuck there. If there's really short, then it's easy for one to break free and for them to fray and stuff like that. So that's why the longer fibers, that's why we end up with cotton and flax and stuff like that for really much later time. We could have it this early, but we haven't found it. But those are other ones we could use.
Okay. So Shannon asks, you mentioned before that Neanderthals had language, and I might say that, you think Neanderthals had language. What is the evidence for that?
Well, language is something that doesn't show up archaeologically. We cannot see it. So when I say I think Neanderthals have language, I'm partially going on along those logical means that a little while ago I said you have to find evidence to back it up.
Right.
But I do think the string is an interesting argument. The way the complexity and the cognitive stuff that's going on there. And the other things that I think about is when I look at Neanderthals, or any time we're recreating an early hominin, do the abilities we ascribe to that hominin create a creature that could live in its environment and accomplish what it did? So can Neanderthals make string, hunt animals, catch fish without language, without cooperation, without communication? I really don't think so. I really think that we've got animals communicating all kinds of stuff to each other. We don't know what all it means, but there's all kinds of communication going back and forth there. There's got to be communication. And then the other thing I'll say is, now that with ancient DNA, we've got more and more evidence that in the late Pleistocene, there's a lot of interbreeding going on. Then if modern humans, who we assume have language, but we also haven't shown, and Neanderthals are going to get together and have babies, chances are that Neanderthal could talk. Chances are you're not showing up going, hey, this is a great catch I got over here. This is one of the mute and doesn't know how to communicate, and let's have babies. Doesn't make sense to me.
So the only thing I was thinking about, sort of devil's advocate, is, can any of these things be done just by imitation? Like, yeah. How would you figure that out, I guess?
That is a good question. You could do this by imitation. It takes a long time, but that's the way a lot of things, when you go back to apprenticeship and stuff like this, there's a lot of learning by imitation without active teaching. But when we start seeing more and more evidence that even among chimps we're seeing active teaching, then you could do it that way. It would be a very inefficient way. And chances are the arguments against language just fall flat for me. They just don't make any sense. So
Here's a different question from Rob who says, Hi, Bruce. Years ago, a Mahali chimpanzee was found to wear a knotted monkey skin necklace, which was presumably knotted by accident. Do you know of any other examples of knots created by non-human animals? I'm not sure if bird nests or things like that involve knots.
Whew, that's tougher. Birds'
Hmm.
nests certainly involve interweaving of things.
Okay.
To get a knot, part of it you got to define a knot. You got to
Mm-hmm.
you got to kind of pass something back around and through itself.
Mm-hmm.
And I'm sure there are examples of natural knots occurring when you've got a whole bunch of fiber, but some of it may just be that fiber gets tangled up so much. Think about it when you've got a coil of rope and it gets all, or string or something, it gets all this, and you're pulling on it, pulling it, and you can't get it apart. It's not really a
Mm-hmm.
knot,
Mm,
but there's just so much tangled up in there that it can't pass through each other.
yep.
I don't
Mm-hmm.
know, actual knots. I would, to find a knot on this stuff that I'm looking at, just be, that would be crazy if I could find a knot. I found strings, so that's great, but finding a knot would be, oh wow, that'd be so cool.
Awesome. Shia asks, is there anything like imaging, mass spec, or multispectral photography that could detect the traces of plant matter on a rock surface when the physical material has decomposed?
I'm gonna say maybe.
Mm-hmm.
Part of the problem is that we've got all kinds of cool technology for imaging and doing various sorts of things.
Mm-hmm.
It may not have been applied in this type of situation.
Mm,
When I work with my colleagues in physics or chemistry, and I say, hey, I want to do this, you've got a machine that does that. And they're like,
mm-hmm.
oh, well, I, I guess we could do it. Maybe. I don't know. And we try to do it, and it usually takes a lot of work to get it to because the stuff we're looking at is so decayed and everything else. I think it's a great
Mm-hmm.
idea, and I think
Mm,
we could do some stuff like that. Certainly, there was some stuff published very recently, past couple of weeks, from groundstone tools at about 32,000, where they were detecting plant fibers from a plant similar to woad, that has a blue pigment to it. But there, the fibers were still there.
okay.
The fibers were
Mm-hmm.
still there, so we weren't trying to find the impressions of fibers. Although I will say that some of the things that I see on the stone tools that I'm looking at,
Mm-hmm.
sometimes it looks like the remnant of something that was there,
Mm-hmm.
but
Mm-hmm.
not the actual thing itself. It's like not exactly mineralized, but the shadow of it's still there. Or
Mm-hmm.
I'm not sure, because then we have to find the technique that can go in and say, well, what is that actually made of?
Right. Mm-hmm.
And if I had a machine that would do that, I would be doing that all the time. But I haven't yet found that ability.
Yeah.
It's a great idea. Hopefully we'll find a way to do something like that.
And I wonder if like starting even with experimentally where you like sort of almost make those impressions in a sense and then like take the material away and see what's left. I don't know. Maybe there's something.
The problem is the time depth difference.
Yeah. Mm-hmm.
I've done a lot of stuff with experimental things, and
Mm-hmm.
we 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 weave together plant fibers, and then we put a stool, wrap it around the stone tool, and then we bury it in the ground, and we come back years later and we dig it up, and I can see changes that occur. A lot of these things shrink down a whole lot, they change,
Cool.
but you can
Mm-hmm.
still see the structure to them. It's giving me clues about what the degradation is going to look like.
Mm-hmm.
She nods.
But and maybe I have to rely on the fact that one of the reasons why this stuff might preserve the way it does, for me to be able to find something like the string, is you get something that's sealed,
Yeah.
set it
Mm-hmm.
on top, and then it stays,
Mm-hmm.
and it
Mm-hmm.
doesn't. Nothing else happens. That maybe a lot of the change that's occurring is fairly rapid, and then from there you get fairly stabilized. And as long as that's not preserved, I'm thinking about the string. I've got a piece of rock here, and the
Mm-hmm.
rock's about this big, and the string's right in the middle on the other side, and it's sitting like this. So you got groundwater coming in, you got roots growing in, and it's the rock is providing a shield
Yeah.
what is underneath there. I don't know for sure because we can't simulate deep.
Right.
That's the problem.
That's always the problem, right? No.
Yeah.
So just Abby wanted to chime in and say, I think that there are birds who can tie knots, weaver birds. So maybe.
I just it's beyond my
Yeah.
knowledge. I'm not a weaver. I've thought about
Yeah.
those weaver birds immediately, and I know they're weaving it together.
Hmm.
I'm just not familiar enough to know if they're actually like, like
Yeah.
tying things through and doing stuff. It wouldn't surprise me. We underestimate our ancestors. We underestimate animals as well. We always
Yeah.
think we're the only ones that can do this stuff.
Right. I have another behind the scenes question. And this one is from me as I was writing. I really love the way that you walked us through being able to infer boats by basically archaeological sites that you cannot get to from here to there without water crossings. Are there other examples of inferences that we can make related to fiber and cordage technology made of perishable materials without the actual evidence preserved? And what evidence would we need to make those inferences more solid? Clothing was the first thing that came to mind for me, but like I don't know, are there other
So
um
the clothing one gets a little bit complicated because we don't string can be used for clothing, but of course
mhm,
we've got animal hides and other things like that
right.
clothing as well, and we can
Yeah.
infer clothing being necessary based on temperatures, unless you're just
Mm,
going to say, you know,
right.
like Neanderthals are just running around, waking up in the middle of the night and doing calisthenics, so their BMR doesn't drop too low and they freeze, which
Right.
has been pointed out sometimes. Um, the stuff about that we were talking about before about the need for being able to carry things. But
Mm-hmm.
again, I think you can infer that when we're seeing
Yeah.
raw material that's being transported long distances, tens of kilometers, 30 kilometers,
Mm-hmm.
100 kilometers. How are you carrying that stuff?
Mm-hmm.
Again, you can fall back on animal hide as the way to do that.
Mm-hmm.
Pretty labor intensive. If you saw Leaky there, if you're as good as him, you can make a lot of string really
Yeah,
fast. If you're as good as me,
exactly.
it's going to take you a while. But
I
that's
always joke like I can barely make Oldowan tools. So anybody who can do anything, make a hand axe or beyond is just, hats off. So
Bruce nods.
Here's a sort of unrelated question that actually came in for me, who asks, are there jobs in natural history museums for registrars or collections managers, and do they require master's degrees or lab experience? There absolutely are. They're incredibly important jobs. And yes, they often do require specialized degrees, lab or other experience. And so maybe I'll see if I can follow up and provide some more information to the person that asked that question about that. But yes, definitely natural history museums are definitely places for registrar and collections manager opportunities. I think we are all set with questions, so I will wrap up. And so I will conclude today's virtual program, which I found fascinating. So please join me in thanking Bruce for sharing his work with us. I'd also like to give special thanks to those who made this program possible, to our behind the scenes team who helped sort through your questions, including Dr. Ryan McRae, who works with us at the Human Origins Program, to our donors, volunteers, and viewers like you. And finally, to all our partners who help us reach, educate, and empower millions of people around the world today and every day, we thank you. So stay tuned, check your email for information about October's Hot Topics webinar, which we'll send directly to you soon. We've put a link in the Q&A where you can find information about our upcoming programs and how to sign up for the museum's weekly e-newsletter. That's the best way to stay informed on upcoming programs and learn more about the museum's research and exhibitions. Right after this webinar ends, you'll see a survey pop up asking for some feedback about the program. Please take a moment to respond. We're very curious to know what topics you might be interested in seeing for future programs, and we appreciate your input. And in fact, in case Joe is in the audience, who actually was the person who suggested this topic and said he had seen one of our previous Hot Topic webinars, he was really interested in this topic, and I said, I know the perfect person. So please, we welcome your suggestions for topics for our future Hot Topic programs. And again, thank you to Bruce, to Dr. Hardy. Thank you to the participants. Thank you to the audience, and we will see you next month.
Briana smiles and waves. Text. National Museum of Natural History, Smithsonian.